Okay, good morning students. Today we will discuss about the elastic constants. So all these in the earlier classes I have told you about the elastic constants like Young's modulus, rigidity modulus, Poisson's ratio. So we will discuss today what is the relationship between those elastic constants, and we will have one problem on that. So here elastic constants are always defined within elastic limits. So I have explained you about the stress strain curve. So in that stress strain curve, I have showed you the elastic limit part, that is the linear part. Within that elastic limit only all these constants are defined. So just we will revise it. Young's modulus is defined as linear stress to linear strain. Linear means along the length. Along the length, whatever stress develops perpendicular to the area, that is your linear stress, which is given by P by E. See here, P by E. Then linear strain, it is the strain along the length. So strain is defined as change in length divided by original length. So that is delta L by L. So if it is tension force, delta L is elongation. If it is compressive force, delta L is contraction. L is the initial length. Then second constant is G, which is called as rigidity modulus or modulus of rigidity. So here it is defined as the ratio of shear stress to shear strain. So I have explained here the diagram of shear stress. If you consider the element here, shear force is a force which acts tangential to the area. So this area is called as shear area. So shear area I have denoted as AS. F is the shear force, like this. It is acting over this area, AS, shear area AS. The ratio of F to AS is called as the shear stress. Shear strain means it is the angular deformation. Due to this, what happens, if the force is acting like this, there will be a lateral deformation here, deflection here, delta, and an angle will be created here, gamma. So this gamma is called as the angular deformation. This point, suppose if this point is A, it gets shifted to A dash. Similarly, if this point is B, this gets shifted to B dash. This I have explained in the earlier classes. So this A dash or B dash is delta. So this delta divided by this H gives the value of gamma, because gamma is very small. Gamma will be equal to tan gamma. So tan gamma will be delta by H. So you can see here. That is why gamma is delta by H, which has no units. So delta will be in mm, H also will be in mm, it has no units. So ratio of shear stress to shear strain is called as rigidity modulus. So its unit will be Newton per mm square. Now the third elastic constant is Poisson's ratio, mu. Also it can be written as 1 by m, where m is a number, whole number. So it is defined as the ratio of lateral strain to linear strain. Lateral strain, epsilon lateral. So lateral strain means, in this diagram, you can see in this diagram, I can show here both linear strain as well as lateral strain. So linear strain is delta L divided by L, whereas lateral strain is delta D divided by D. So when tension force acts on a material or a specimen, elongation takes place, that is length will increase, whereas diameter reduces. Here delta is the reduction in the diameter. If compressive force acts on the same member, then length will be decreased, diameter will be increased. So here delta N is the increasing length, delta D is the decreasing diameter. When tension force is acting, P is the tension force, then we can define lateral strain as delta D by D, linear strain as delta N by L. So the ratio of this lateral strain to linear strain, this is called as Poisson's ratio. Normally it is less than 1. Actually the maximum value of mu is 0.5, that we can prove. Now next one is, we have to define one more elastic constant called K, which is defined as the ratio of bulk stress to volumetric strain. So whenever bulk modulus of elasticity comes into picture, so we have to define in terms of volume. So here bulk stress, for this I have written this diagram. this is a solid figure where the initial dimension x, y, z I have taken. So initial volume will be x into y into z. Once it is subjected to some tension force. So due to the tension force, stress will develop. So that stress, we can take it as sigma, which is called as bulk stress because it is acting in all the three directions, and I am taking that sigma constant in all the three directions, x, y, z directions. So here, whenever you are defining bulk stress, we have to talk three dimensional like this. Example for this is fluid. A fluid pressure will be like this. In all the three directions it will be there. Now here, when it is subjected to tension, naturally there will be change in volume. So that change in volume will be delta V. So the delta V by V is nothing but your volumetric strain. So bulk stress divided by volumetric strain, which is change in volume divided by initial volume, gives the value of that bulk modulus. So its unit also Newton per mm square. If you observe all these four elastic constants, E, G and K all have the same units, Newton per mm square or MPa, whereas Poisson's ratio is a constant. It doesn't have any units. Now we can see the relationship between these elastic constants. So there are four elastic constants which we can define within elastic limits. They have got relationship among them. The relationship can be derived in these three forms. So first equation is E is equal to 2g into 1 plus mu. Second equation is E is equal to 3k into 1 minus 2 mu. Third equation is by combining these two, by eliminating mu, you can get the third equation where E is equal to 9gk divided by g plus 3k. So the advantage of using these equations is if you know any two elastic constants, the other two can be found out. For example, if you know E and mu, G can be found out. If you know E and mu, K can be found out. Or if you know G and K, E can be found out using this, and afterwards mu can be found out using any one of these two equations. So there are four elastic constants E, G, mu and K. Out of four, using any two equations, we can find the two unknowns by knowing the two elastic constants. Now I have taken a problem here. So this is an important problem from the examination question paper. You can see here he has given a cylindrical bar like this. It is subjected to a tensile force of 20 kilonewton, tension force. Okay. The length of the bar is 150 mm. That is called as the gauge length. Diameter, initial diameter of the bar D is 12 mm. Now he has given the value of elongation delta L 0.3 mm and decrease in diameter delta D 0.0079 mm. So due to this, what happens? Length will increase whereas diameter reduces. So the bar takes a shape like this. So the elongation delta L is 0.3 mm and change in diameter, that is decrease in diameter, is 0.0079 mm. It is very small. So question is determine the elastic constants. So a bar of diameter 12 mm having length 150 mm is subjected to a tensile force of 20 kilonewton and the elongation is observed as 0.3 mm and decrease in diameter is observed as 0.0079 mm. Calculate the elastic constants. So that is the question here. Now what we have to do is, we know these relations. Out of these four, you have to get any two from this data and the other two can be found out using any two of these equations. Now let us see how we can tackle this problem. So he has given the diameter, let us find out the area, cross-sectional area of the specimen. So pi d square by 4, this is a circular or cylindrical rod. So therefore cross-sectional area is given by pi d square by 4. If you substitute d as 12 mm, you will get 113.1 millimeter square. Now once you know the force acting, tension force acting on the bar and the cross-sectional area, that force itself will act as a resistance force which is going to develop within the body. That resistance force divided by the cross-sectional area gives the linear stress. So force is acting like this. So it is called as axial force. See here, I have written here. P is called as axial force because it is acting along the axis of the bar. So here linear stress is given by the resistance force divided by cross sectional area. If you substitute the force as 20 kN means 20 into 10 power 3 Newton. Everything should be converted to Newton and millimeters because the stress value will be in Newton per millimeter square. So if you substitute and simplify, you will get 176.8 Newton per mm square. Then linear strain is given by delta L by L. I have explained here delta L by L. So here delta L is given 0.3 mm. Initial length of the member is 150. So 0.3 by 150, which comes out to be 0.002. No units for this. No units for strain. Now once you get sigma linear and epsilon linear stress and linear strain, you have to take the ratio to get the Young's modulus. So E is 176.8 divided by 0.002. You are going to get 88,420 MPa or Newton per mm square. Definitely it is not steel. It is some other material. Let us not worry about the material. So if for steel you have to get 2 into 10 power 5 or 2.1 into 10 power 5 Newton per mm square. It is not steel bond. Then to find out the, so E value is known now. Then to find out mu value, you have to get the lateral strain. So lateral strain is given by epsilon lateral is equal to delta D by D. So change in diameter divided by initial diameter 0.0079 by 12. You are going to get this value 6.58 into 10 power minus 4. That also doesn't have any units. Now Poisson's ratio mu or 1 by m is given by lateral strain to linear strain ratio. So if you substitute these values and simplify, you will get 0.33. So 0.33 is the value of Poisson's ratio for this material. Next, once you get these two, now using the first equation, you can find out G. Using the second equation, you can find out K. So E and mu are known now. I am going to use the first equation. E is equal to 2G into 1 plus mu. So G will be E divided by 2 into 1 plus mu. So if you substitute the values and simplify, you are going to get 33,266 point something. So Newton per mm square. That is the value of rigidity modulus of the material of this bar. Then bulk modulus of elasticity you can get from the second equation. Here also E and mu are known. So you have to find out K. So K will be E divided by 3 into 1 minus 2 mu. So mu is 0.33. So E value is this. If you substitute and simplify, you will get 86,179 point something Newton per mm square. That is the value of bulk modulus of elasticity. So by knowing any two elastic constants, you can always find out the other two constants using these relationships. So this is about the relationship between the elastic constants. Thank you.